Bismillahirrahmanirrahim. Assalamu alaikum, dear viewers. Welcome to Physics Mathematics Hub. My name is Sajid Alam and I am here to make physics and mathematics concepts easy and enjoyable for you. Today we are solving problem 1.30 from the book of Quantum Mechanics Concepts and Applications by Nouredine Zettili. Here is the statement. Consider a tenfold ionized sodium ion Na plus 10, which is obtained by removing 10 electrons from a sodium atom. Tenfold ionized sodium ion is shown in the figure, where 10 electrons are removed from the sodium atom. In part A, we have to calculate the orbiting speed and orbital angular momentum of the electron with respect to the ion's origin when the ion is in its fourth excited state. In part B, calculate the frequency of the radiation emitted when the ion deexcites from its fourth excited state to the first excited state. So let's get started. We are given that a tenfold ionized sodium atom having number of photon is equal to 11 and electron equal to 1. Ion is in fourth excited state, for which n is equal to 5. Transition from fourth excited state to its first excited state. For fourth excited state, we put n is equal to 5, and for first excited state, we put m is equal to 2. We are required that orbiting speed of electron, denoted by v, and orbital angular momentum, denoted by capital L. In part B, we have to find the frequency of the radiation from fourth to first excited state, which is denoted by nu. First, we solve part A. To calculate the orbiting speed of the electron in its ninth excited state, we set the absolute value of binding energy of the nth excited state equal to the kinetic energy of the electron. So the equation is given as kinetic energy is equal to En, where En is the binding energy of the nth excited state. Kinetic energy is equal to 1 over 2 me v square, which is equal to z square into r divided by 1 plus me divided by capital M into n square. In this equation, on the left side, we see the kinetic energy of the electron given by 1 over 2 mv square, where me is the mass of the electron and v is its velocity. On the right hand side, we have the absolute value of binding energy of the electron. Here Z is the atomic number and R is the Rydberg constant. The denominator consists of n, which is the principal quantum number, and a correction term for the reduced mass, where me is the electron's mass and capital M is the mass of nucleus. This whole term is approximately equal to 1. So we get 1 over 2 mv square is equal to z square into r divided by 1 multiplied by n square. Solving the equation for v, we get v square is equal to 2z square r divided by mass of electron into n square. Now we will take square root on both sides. We get V is equal to Z divided by N into 2R by mass of electron square root, where Z is the atomic number of ion. Here for sodium, Z is equal to 11. N is equal to principal quantum number. For the fourth excited state, we put N is equal to 5. R is the Rydberg constant having value 13.6 electron volt. Mass of electron is denoted by Me, which is equal to 0.511 mega electron volt per c square. Putting all the values in the above equation, we have V is equal to 11, where 11 is for Z and 5 is for N. 2 multiplied by Rydberg constant, which is 13.6 electron volt, divided by mass of electron, which is 0.511 mega electron volt per c square square root. Here on the right hand side, 2.2 is multiplied by a square root. Inside the square root, we have a fraction. The numerator is 27.2 c square, where c represents the speed of light, approximately equal to 3 multiplied by 10 to the power 8 meters per second, and the denominator is 0.511 multiplied by 10 to the power 6. After simplifying the above fraction, we get V is equal to 2.2 square root 53.2 multiplied by 10 to the power minus 6 multiplied by C. In the next step, calculating the square root, we get 2.2 multiplied by 0.00729 multiplied by speed of light. After finding the product, we get V is equal to 0.048 multiplied by 10 to the power 8 meter per second. In scientific notations, we can write this as 4.8 multiplied by 10 to the power 6 meter per second, which is the required answer. Therefore, the orbital speed of the electron is 4.8 multiplied by 10 to the power 6 meters per second. Now, we are going to calculate the orbital angular momentum. We use L is equal to n h cut, where L is the orbital angular momentum, n is the principal quantum number. Here for the fourth excited state, n is equal to 5 and h cut is the reduced Planck's constant, equal to 1.055 multiplied by 10 to the power minus 34 joules second. Plugging all the values in the above equation, we have L is equal to 5 is multiplied by reduced Planck's constant. Finding the product, we get L is equal to 5.275 multiplied by 10 to the power minus 34 joules seconds. Thus, for n is equal to 5, the orbital angular momentum of electron is 5.275 multiplied by 10 to the power minus 34 joule seconds. In part B, we have to find the frequency of the radiation from fourth to first excited state. So first we will find the energy, which is equal to E, that is equal to En minus Em. Putting the values, E is equal to h nu, En is equal to the binding energy of the nth orbital, and this is the bonding energy of the nth orbital. We take z square and r as common. We get minus 1 over n square. Here minus into minus become plus 1 over m square. Z square multiplied by r divided by h, which is the Planck constant, multiplied by 1 over m square minus 1 over n square. Plugging all the values in the above equation, we get 11 square multiplied by r, which is 13.6 electron volt, divided by Planck constant, which is 4.136 multiplied by 10 to the power minus 15 electron volt seconds. 1 over m square is equal to 1 over 2 square minus 1 over 5 square. We get 121 multiplied by 13.6 divided by the Planck constant into 1 over 2 square. We get 4. 1 over 5 square, we get 25. Multiplying the above numerators, 121 multiplied by 13.6, we get 1645.6, divided by the Planck constant. 1 over 4 gives 0.25 and 1 over 25 gives 0.04. Dividing 1645.6 by 4.136, we get 397.87, multiplied by 10 to the power plus 15 and multiplied by 0.21 hertz. After finding the product, we get 83.55 multiplied by 10 to the power 15 hertz, and in scientific notation we can write this as nu is equal to 8.36 multiplied by 10 power 16 hertz. Therefore, the frequency of the radiation is 8.355 or 8.36 multiplied by 10 to the power 16 hertz. In this video, we calculated the properties of a tenfold ionized sodium ion in its fourth excited state. The electron orbits at a speed of about 4.8 million meters per second, which is a significant fraction of the speed of light. The orbital angular momentum is quantized and calculated to be 5.275 multiplied by 10 to the power minus 34 joule second, illustrating the quantum mechanical nature of angular momentum. When the ion deexcites from the fourth excited state to the first excited state, it emits radiation with a frequency of approximately 8.34 multiplied by 10 to the power 16 hertz, which lies in the ultraviolet region of the electromagnetic spectrum. This is a remarkable demonstration of the quantum behavior of hydrogen-like atoms. That is it for today's calculation. We have explored the fascinating case of the tenfold ionized sodium ion and seen how removing 10 electrons transforms the atom's properties. If you found this video helpful, don't forget to like, share, and subscribe to Physics Mathematics Hub. For more interesting physics and mathematics problems, stay curious, keep learning, and see you in the next video with the next problem. Allah Hafiz.